Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad ARSYAD bin AZAHARI and my matric number is 2311901. And here with me is
My name is MAJID with the ZAFRI. The number 2312861.
so for the content of this video is the production and application of first is X-ray, second is electron microscope, third is laser, fourth is Bainbridge mass spectrometer, and the last one is the microwave. For the production of X-ray, X-ray are a form of electromagnetic radiation with wavelength shorter than ultraviolet light but longer than gamma rays. Wilhelm Conrad Röntgen discovered X-rays in 1895, and their ability to penetrate various materials made them valuable in medical imaging, industry, and scientific research. The production of X-rays involves the interaction of high-energy electron with matter, typically in an X-ray tube. So the first thing is the electron source. X-ray tubes consist of a cathode and anode. The cathode emits electron through a process called thermionic emission. It involves heating a filament to release electron into the surrounding space. Next is the acceleration of electrons. The released electrons from the cathode are accelerated towards the positively charged anode, usually made of tungsten, by applying a high voltage across the tube. The voltage can range from tens of thousands to hundreds of thousands of volts. Next is the interaction with target material. When the accelerated electrons strike the anode, they interact with the target material. In most medical X-ray tubes, tungsten is used as the target material because of its high atomic number, which enhances the X-ray production. Next is the Bremsstrahlung radiation. The primary method of X-ray production is through Bremsstrahlung radiation, which is in German for braking radiation. When a high-speed electron approaches the positively charged nucleus of a tungsten atom, it experiences a deceleration or braking effect. This sudden change in speed causes the electron to emit energy in the form of X-rays. Another way X-rays are produced is through the ejection of inertial electrons from tungsten atom. This process is producing a characteristic X-ray. The electrons from the outer shells then fill the vacancies, releasing characteristic X-rays in the process. The combination of Bremsstrahlung and characteristic X-rays forms a continuous X-ray spectrum. The X-ray beam generated is heterogeneous, containing a range of energies. For the application of X-ray, it involves in medical imaging, such as in radiography, X-ray imaging. X-rays are intensively used in medicine to produce image of the internal structure of the body. Common applications include detecting fractures, assessing joint conditions, and examining the chest for lung and heart condition. It also involved in computed tomography. CT scans use X-ray to create detailed cross-sectional images of the body, providing three-dimensional information. They are valuable for diagnosing conditions in the head, chest, abdomen, and extremities. Next is the dentistry. X-rays are widely used in dentistry for imaging teeth and the surrounding structure. Dental X-rays help identify cavities, assess tooth development, and plan for procedures such as extraction or orthodontic treatment. Then in industrial radiography, in non-destructive testing, X-rays are employed to inspect the integrity of materials and structure in industries such as manufacturing, construction, and aerospace. This is crucial for identifying defects, cracks, or inconsistencies in weld pipelines and other components. Next is in security screening. X-ray scanners are used for security screening at airports and other high security locations. They can detect hidden objects in baggage or on a person, providing a non-intrusive method for security checks. They also involve in scientific research. X-rays are employed in various scientific disciplines to study the structure of materials at the atomic and molecular levels. Techniques like X-ray crystallography are used to determine the three-dimensional structure of molecules, including biological macromolecules like protein and nucleic acid. They also involve in material analysis and quantity control. X-ray fluorescent (XRF) spectroscopy is used to analyze the elemental composition of material. This is valuable in fields such as archaeology, geology, and quality control in manufacturing. So the next element we are going to learn is about the production and application of electron microscope. Electron microscope is a powerful imaging tool that use a beam of electron rather than light to magnify and visualize objects at much higher resolution than traditional light microscope. There are two main types of electron microscope, which are transmission electron microscope (TEM) and scanning electron microscope (SEM). So for the production of and how the electron microscope works is, the first thing we have electron source. The key component in an electron source, typically a tungsten filament or a field emission electron gun. The electron source is responsible for producing a high-intensity beam of electron. Next, we have the electron gun. In TEM, the electron gun is used to generate a parallel beam of electrons. In SEM, the electron gun is designed to scan the specific surface. We also have the electron lens. A series of electromagnetic lenses are used to focus and manipulate the electron beam. The lenses include condenser lens and objective lens. Next, we have the vacuum system. Electron microscope operate in a vacuum to prevent the scattering of electrons by air molecules. A complex vacuum system is integrated into the microscope. We also have the specimen chamber. The specimen to be examined is placed in a chamber. In TEM, the specimen needs to be thin and transparent to electron. In SEM, the specimen is coated with a thin layer of metal to enhance conductivity. We also have the detectors. Detectors capture signals generated by the interaction of electron with the specimen. These signals are then processed to create the final image. And lastly, we have the control system. The microscope is controlled by a sophisticated system that manages the beam, focus, and other parameters. Modern electron microscopes often have computer interface for precise control and automation. For the application of electron microscope, such as in biology and medicine, electron microscopes are widely used to study the ultrastructure of cells and cellular components. Researchers can visualize organelle, cell membrane, and other cellular structure in great detail. Next, in material science, electron microscopes are essential for characterizing the structure and properties of materials at the atomic and nanoscale. These include metals, polymers, and ceramics. Electron microscope also is used in nanotechnology because it plays a vital role in the development and characterization of nanomaterials. Next, in environmental science, electron microscopes are used to study particulate matter in the atmosphere and environmental samples. It also involved in the pharmaceutical research. Electron microscopes are used to analyze the structure of drug compounds, study drug delivery system, and investigate interaction with biological tissues. Lastly, electron microscope is applied in entomology and zoology. Electron microscope aid the entomologists and zoologists in studying the detailed morphology of insects and other small organisms.
Next, moving on to the next topic, we will be discussing about laser. So, how does laser work? First, energy source. The laser requires an external energy source to pump energy into the system. Second, active medium. The laser medium is a material that can amplify light. One of the common medium used is a ruby rod medium. Third, population inversion. Population inversion occurs when more atoms or molecules are in higher energy states than in lower energy states. Fourth, stimulated emission. When an atom or molecule in the higher energy state is stimulated by an external photon, it can emit a second photon of the same frequency, phase, and direction. Fifth, feedback mechanism. The ruby rod medium is placed between two mirrors, forming an optical cavity. One mirror is highly reflective, and the other is partially transparent. The arrangement provides a feedback mechanism, allowing photons to bounce back and forth between the mirrors. Sixth, amplification. As photons pass through the ruby rod medium, they stimulate the emission of more photons with the same properties. This results in the amplification of light within the optical cavity. And lastly, laser emission. Eventually, a cascade of stimulated emissions leads to a coherent beam of light emerging through the partially transparent mirror. This intense, monochromatic, and directional light is the laser beam. There are many applications of laser, such as for communication. Lasers are used in fiber optic communication systems to transmit data over long distances with high bandwidth and minimal signal loss. Lasers are also used in medical procedures. In medicine, lasers are employed for various purposes such as surgical procedures, eye surgeries, LASIK, dermatology, skin treatments, and dental treatments. Lasers can also be used for defense and security. They have applications in defense systems, including laser guidance for munitions, range finding, and even directed energy weapons for certain military applications. Moving on to the next topic, we will be explaining about the Bainbridge mass spectrometer. Before we delve deeper into this topic, we should know first what is the function of mass spectrometer. Mass spectrometers can be used to identify unknown compounds via molecular weight determination, to quantify known compounds, and to determine structure and chemical properties of molecules. So, the working principle of a Bainbridge mass spectrometer are as follows. Ions are formed at D and pass through the cathode C and then through a slit S1. They then travel between two plates A and B, between which a potential V is applied. A magnetic field strength B is applied at right angles to the electrostatic field, and so the electrostatic and electromagnetic forces act in opposite directions to each other. A particle with a charge q and velocity v will only pass through the next slit S2 if the resultant force on it is zero, that is, traveling in a straight line. That is, if the electromagnetic force is equal to the electrostatic force. Therefore, for the particle to pass through S2, velocity of particle is equal to the electric field strength over the magnetic field strength. But this is a constant, and so only particles with a certain velocity enter the deflection chamber F. For this reason, the combination of slits and deflecting plates is called a velocity selector. In the deflection chamber, the ions are affected by the magnetic fields alone and so move in circular paths, the lighter ions having the larger path radius. The radius of the path in the deflection chamber is directly proportional to the mass of the ion. The detection is by either a photographic plate or a collector that produces a small current when the ions fall on it. The magnetic field may be varied, so changing the radii of the particle's path so that ions of different masses fall on a fixed collector. This method of analysis is very accurate and can detect differences in the masses of two ions as small as 1 part in 10 to the power of 9. Mass spectrometer also has a wide variety of uses such as identification of compounds. Identify unknown compounds by analyzing their mass spectra and comparing them with reference database. They are also useful for pollutant detection. They are used to detect and quantify pollutants and contaminants in air, water, soil, and other environmental samples. Drug testing is another example. It is widely used for detecting drugs and their metabolites in forensic toxicology. Mass spectrometers are also used in the food safety division to detect contaminants and ensuring the safety of food products. They are also used for geological and archaeological studies, which is to determine isotopic ratios to study the origin and history of geological and archaeological samples. Lastly, mass spectrometers are also used for clinical chemistry, for analyzing blood and urine samples for diagnostic purposes. And to our last topic, which is microwave. The production of microwave are as follows. The generation of microwaves involves the conversion of electrical energy into electromagnetic waves with frequencies in the microwave range, typically around 2.45 GHz. The most common method of generating microwaves is through a device called a magnetron. The magnetron are as shown in the diagram below. So, how is microwave produced? We can see the flow we can see the flow electron emission. A magnetron consists of a cathode, negatively charged electrode, and an anode, positively charged electrode. Electrons are emitted from the cathode through a process called thermionic emission or electron gun effect. Magnetic field. The magnetron has a strong external magnetic field, typically provided by permanent magnets or electromagnets. This magnetic field causes the emitted electrons to move in circular paths. Next, electron interaction with resonant cavities. The magnetron also contains resonant cavities, or hollow chambers, made of conducting material. These cavities are arranged in a specific geometric pattern. As electrons move through the magnetic field, they interact with the resonant cavities. The geometry of the cavities causes the electrons to experience a force that leads to the emission of electromagnetic waves. Resonant frequency. The arrangement of the resonant cavities and the strength of the magnetic field are designed to ensure that the electrons oscillate at the resonant frequency of the cavities. The resonant frequency is typically in the microwave range, and as a result, the emitted electromagnetic waves are microwaves. And lastly, microwave output. The oscillating electrons produce a high-frequency alternating current within the magnetron, and this current generates electromagnetic waves that are emitted through an output antenna. There are various applications of microwaves in daily life, such as cooking. Microwave ovens heat food by causing water molecules in the food to vibrate, generating heat. Microwaves are also crucial for long-distance satellite communication. Other than that, microwaves are also useful for radar systems, for air traffic control, weather monitoring, and military surveillance. Microwave are also useful for Wi-Fi and microwave links for high-capacity data transmission. And lastly, astronomy is also a division where microwave is commonly used, such as the telescope. Telescopes sensitive to microwave frequencies provide insights into cosmic phenomena. And by that, we have reached the end of our video. Thank you for listening and giving us your time. Assalamualaikum warahmatullahi wabarakatuh.